And when you follow the various terms, basically this term came from this term in the discrete case. And when we looked at the discrete case in terms of the annihilation creation operators of the oscillators, we had seen that that term is responsible for the diffusion of particles. So if you, when I mean particles, just understand not the oscillators themselves, but the packages, energy packages that each one of those oscillators can have. I can have an arbitrary number of packages in any of these oscillators, but at the end of the day, the number of oscillators is fixed. In a sense, at every space-time point, I'm assigning some kind of an oscillator. Number of space-time points is fixed, it doesn't change, but the number of packages can change. I can have states which has one package here, another package over there. I can have another state that has 100 packages over here. And if, let's say, if I start with a state that has 100 packages over here, as time evolves, these packages will just diffuse around. So I will have these packages moving around due to these terms. There are no interactions yet. These packages do not hit each other, transfer momentum, etc. They just move around, they just diffuse. Now, the reason why I'm trying to emphasize, now this is my field theory, by the way. This is what we call the field theory. And the reason why I want to emphasize this connection with the collection of oscillators is you already know how to quantize the oscillators. But if you know how to quantize the oscillators, we know how to quantize the fields. There won't be anything fancy. Of course, now we don't have just a single oscillator. That is what you are used to in quantum mechanics. We will have infinitely many oscillators. We have to quantize all of them. And the next of this and next semester will be, okay, if we quantize these fields with these infinitely many fields, infinitely many oscillators, what will they tell us? Now, this is, to be more precise, this is called the scalar field theory. Because why? Well, because I started by saying oscillators, and the oscillators was this, whatever this x represents is the displacement from the equilibrium. I started to help you visually. I just started with a collection of oscillators which just oscillate in real space, but they don't have to oscillate in the real space. For example, just consider the electric field. Electric field oscillates at every point. If you have a light, that is nothing but an oscillating electric field. At every point, there's something that is oscillating, but it's not oscillating in real space. I mean, it's just the magnitude of the electric field is oscillating back and forth. Its direction might be oscillating back and forth. So that is what is oscillating. So electric field, well, let me say the vector potential, the vector field, not the electric field itself. We have the scalar field and the vector potential describing the electromagnetic field. For example, that is a vector field. This is a scalar field we will look at. Let me even be more precise. This is a real scalar field. We can have vector fields where the thing that is oscillating is the direction and the magnitude of the vector. We can have complex fields, complex vector fields, complex scalar fields. We can have even spinor fields.
This is the Klein-Gordon, right?
Yep.
Can I write Klein-Gordon with all these different spinor complex vector fields?
Well, if you just say phi is, let me just take phi to be a vector. That is what you will get. You get the Klein-Gordon field for a vector field, for example. But I mean, for an electron, you would rather not do that. You would rather obtain the Dirac equation for electrons. Yeah. All of these we will see. Now, before continuing, the first thing I would like to do, I mean, before even quantizing the system, is if we have this discrete thing, we know how to obtain the equations of motion, right? So basically, from a Lagrangian, you have the Euler-Lagrange equations, which is del X del L by del Qi minus del over del T del L by del Qi dot, this is equal to 0. How do you obtain that? Well, you say that L is a function of Qi and Qi dot. So you have the action, which will be a function of Qi as a function of time t. Then you ask yourself the question, let me change this Qit as a function by a very small amount. Let me look at this one. And requiring this to be equal to 0 for all possible variations, you get the Euler-Lagrange equation. So you all remember that. So this is something that you should have covered in classical physics, in 311 in undergraduate, if you take in analytical mechanics 502, this is also covered there. Well, let's look at over my field theory. We will do more or less exactly the same thing. This is what I call my Lagrangian. Keep in mind that now my Lagrangian depends on my field, time derivative of the field, Lagrangian density, and the position derivative of my field. It depends on all three. My action, I can say that, okay, it's a function of phi, but phi is a function of x and t, will be given as the integral of my Lagrangian. My Lagrangian is itself an integral of the Lagrangian density. Well, let me use this notation, phi prime. Phi dot is del phi by del t, and phi prime is del phi by del y. And we will basically do the same thing. Let me look at the variation of action if I change phi very slightly. I said this will give me phi will be phi plus delta phi dot will be phi dot plus delta phi dot, and phi prime will be phi prime plus delta phi prime minus this thing. Well, I can do the usual thing, this delta phi dot delta phi prime, I will assume that to be very small. I mean, that kind of restricts the kind of variations I have, but whatever the variation is, I want my action to be an extremum point, so the variation of S to be 0 for that variation. So if I assume that to be small, this will give me, let's say, derivative of the Lagrangian with respect to phi plus derivative of the Lagrangian with respect phi dot plus, not phi dot, this is delta phi, derivative of the Lagrangian density with respect to phi dot, the variation of phi dot, plus derivative of the action with respect to phi prime times the variation with respect to phi prime. Okay, now this delta phi dot is nothing but derivative with respect to time of delta phi, and similarly delta phi prime will be the derivative with respect to y of delta phi. I will do integration by parts. Just like in the classical mechanics case, I will get the boundary terms. Those boundary terms, I will assume them to be 0. So I will ignore the boundary terms, and what I am left with is dt dy minus del by del t delta phi, this should be 0 for any variation delta phi. Well, if this is to be correct, this should be satisfied.
John, do we have other theories where these boundary terms aren't set to 0?
You mean other theories where they are not set to 0, or they are?
Yeah, they're not necessarily 0.
Well, you see, in this case, I'm looking at the whole space. I want my fields to be 0 at infinity.
Mm-hmm.
But for example, again, probably you should have covered it in your mechanics courses. You can say that, okay, let me keep the boundary at some arbitrary point. You see, here I'm treating my action as a function of this field. You can also treat your action as a function of the endpoints or the boundary.
Mm-hmm.
Then, for example, if you treat your action as a function of the endpoint of your y integral, then you can actually show that P is equal to del S by del Y. Does this look familiar, by the way? Momentum is the derivative of the action. And so you can play with it if assuming the action to be a function of the boundary, so it does tell you some new tools. And, well, I have learned from your friend over there, for example, there are all these field theories which claim that, okay, if you have a space, the space also, the physics in this space is determined by the physics on the boundary. There's all these duality things. If I'm saying something wrong, correct me.
That's normal.
But that is not something we will cover. So we will start with the basics here. But of course, keeping the boundary might give you some new tools. Okay, there is some point which sometimes gets confusing for the students. For example, when taking this derivative, I am assuming that phi dot is independent of phi and phi prime. Okay. But here, I kind of related them already. So there's nothing wrong, just make sure that you pay attention to your conventions. Now, when I'm talking, you see, this is what I had done. I'm just Taylor expanding this in terms of the arguments of the Lagrangian. So you can think of this as not as the derivative of the Lagrangian with respect to phi dot, but that is the derivative of the Lagrangian with whatever second argument it has. And then once I take the derivative, I set that second argument to be phi dot. So that is what I mean basically over here. When I say, when I'm taking those derivatives, I will treat phi dot, phi prime, and phi independent, mainly because I'm defining my Lagrangian to be a function of three arguments. This is the derivative of the Lagrangian with respect to the second argument. This is the derivative with respect to the third argument. This is the derivative with respect to the first argument. Once you take those derivatives, the first argument will be phi, the second one will be phi dot, the third one will be phi prime. But they are after taking the derivatives. So before taking the derivatives, they are already independent in this derivatives. Okay, so this will be our equation in this one-dimensional field theory we have. Now you see this Lagrangian is quite general. It doesn't even need to have any specific form. Now we can apply this to what we already have. This Lagrangian I have over here. So for our Lagrangian, we have 1 over 2 v squared phi dot minus phi prime squared plus m squared phi squared. This is my Lagrangian with, again, three arguments.
Is it phi dot square? Or?
Square, yes. Well, the derivative with respect to phi is just 2m squared. No, sorry. If I stick with the convention, all these terms have 1 over 2. Is m squared phi derivative with respect to phi dot is 1 over v squared phi dot. The derivative with respect to phi prime is minus phi prime. So my Euler-Lagrange equation tells me that m squared phi minus the time derivative of this one is 1 over v squared d squared by dt squared phi phi, and the third term is plus del squared phi by del y squared, and this should be equal to 0. This is my Euler-Lagrange equation for this field theory, for this real scalar field theory. Does it look familiar?
Yes.
What
Yes.
the,
Klein-Gordon.
That's the Klein-Gordon equation. It's the wave equation. If m were 0, it's the wave equation, and v is the wave velocity. In our case, it will be c. M will turn out to be the minimum energy of the system. But this is nothing but, as you said, the Klein-Gordon equation. Well, what about the solutions of this equation? Well, it is translational symmetric. So I can look for solutions of the form e to power minus I et plus I px, plane waves, sorry, y. I can look for plane wave solutions. If I put this in my equation, what I will get is m squared plus e squared over v squared. Just one moment. E squared plus v squared, and then I have minus p squared. This is equal to 0. I probably missed a sign somewhere. Where did I get the sign wrong? No, the convention, this is positive. If that is positive, and if I did everything correct, this sign over here turns out to be negative. I say m squared is not something we had interpreted yet, so I can play it around. So E turns out to be, let me also set V equal to C will be 0. In my case, they will all be 1.
The problem is this field does not vanish at boundaries, right? But
No.
we assume that it should.
Oh, no problem. I mean, if you want, I can just put a e to the power minus epsilon y squared plus t squared, and take the limit epsilon goes to 0.
You sure it still doesn't vanish?
What do you mean doesn't vanish? It vanishes when y or t, any one of them goes to plus or minus infinity. It does vanish.
Epsilon goes to 0?
Yeah. Eventually, at the end of the computation. Yes, plane waves, you are right, plane waves are kind of a pathological system in the sense that they are not normalizable, but I can express everything in terms of them. So in that sense, they are nice. I can play with them. No, anyway, what I wanted to get to is E squared is equal to P squared plus M squared. So P is the momentum, M basically the minimum energy the system has, M identified as the coefficient of 1 over 2 phi squared. M squared identified as that one is the mass of my particle. if I'm to interpret this E and P as the momentum and the energy. So this is the solution of the Klein-Gordon equation. Now there's one problem though, for those who haven't studied Klein-Gordon equation in quantum mechanics. E is equal to square root of P squared plus M squared, with a plus or minus sign. So we have negative energy solutions. We have states with positive energy and states with negative energy. Now, if you take quantum mechanics 2, or if you have studied Klein-Gordon equation before, there are various tricks that we kind of struggle to make sense out of these negative energy solutions. But in the field theory, I will not go into them, but in the field theory context, we will see that, well, they are quite easy to solve. There's no problem. You see, I'm not talking about wave functions here. I will not be talking about particles with negative energy, but these, my phi will be fields, and I will quantize them. So the interpretation will be kind of obvious once we quantize the field, but this is just something to keep in mind. We have these negative energy solutions in Klein-Gordon field, we have these negative energy solutions in the Dirac field, we have, and I mean, in order just to make sense, Dirac had to invent this concept of the Dirac sea, that the negative energy states are all filled with negative energy electrons, etc. It gives nice physical intuition, but we don't need it in field theory. We won't need it. Now, let's go ahead and try to quantize this. Let me first write the solutions. I know the energies, possible energies, as a function of the momentum. So the general solution of my phi of y of t will be basically, let me use this notation, d squared y. Yeah, eventually I will move to four-dimensional space-time, so that will be d4y, so the generalizations will be kind of almost trivial. Then I have e to power minus I e. Let me write this also plus or minus omega p. Omega p, I will define it to be the positive number, p squared plus m squared. Remember, I'm setting h bar to 0, to 1. If h bar was not 1, this would have been h bar omega p. D squared p minus I omega pt e to power I py, some coefficients of, let's say, p only, plus e to power I
You said we take h equals 0, right?
no,
H bar.
1.
1, okay.
They are all 1.
Otherwise, it would not be possible to write the quantum fields, right?
No. That will be correspond to the classical limit. And of course, I also have omega p squared should be equal to p squared plus m squared. So I don't really have two integrals over both energy and momentum. Energy is already fixed. So I actually only have an integral over the momentum, dp. And just the normalization of these phi p's, I will have the omega p here. These are my solutions. You see, the coefficient of one of the exponents is phi, the coefficient of the other exponent is phi star. They have to be so, because this is a real field. We started with a real scalar field. So phi y of t conjugate has to be equal to phi of y of t. So the conjugate of the first term has to be equal to the conjugate of the second term for my field to be a real field. If it were a complex field, we will also study the complex field. The only modification will be phi and phi star will be just different fields.
At first, and why we write Dirac delta?
You see, these are complete states. These form complete states, since they are the eigenstates of my Hamiltonian. So any function I can write as the sum of my eigenstates. That's the basic, one of the basic premises of my quantum mechanics. Any state I can just write as the superposition of the energy eigenstates, or the eigenstates of any Hermitian operator. But they are energy eigenstates only if E squared is equal to omega p squared. If E squared is not equal to omega p squared, they are not energy eigenstates. So I need to, so in a sense,
That's the condition of quantizing the energy.
in a sense, those functions phi, E, and P, they are energy eigenstates only if E squared is equal to omega p squared. Otherwise, they are not eigenstates of my Hamiltonian. So I need to sum over all phi EPs subject to that condition. Now, why did I include this square root of 2 omega p over here? Why did I write the squares rather than, I don't know, E minus omega p? Well, this won't give, first of all, this won't give me all the energy eigenstates. I should also add the ones E plus omega p. I could have also used this one. But the only thing that will change will be just the normalization of my states. So I can just take these factors of 1 over square root of 2p, redefine my phi p's by changing their normalization. You get rid of that 1 over square root of 2p, 2 omegas. We will see later on why usually they are kept there.
John, I think the two are equal anyways by the properties of the delta function.
Which twos? This one and this one? No, they are not equal.
Or like equal up to a constant.
Yeah.
Right. Right.
Yeah. So part of that constant is already here. Part of that is somewhere else. You see, which one you use, again, I repeat, which one, you can use this one, you can use this one, they will change the normalization of phi, which we have to take into account when we are interpreting our fields in terms of the amplitudes, the probabilities, etc. You can always change the normalization of your wave function. It's not physical, but you have to be consistent in the sense that if in one normalization you interpret phi squared as your probability, and if you change normalization, phi squared will no longer be probability, but you have to scale what phi squared by whatever you choose as your normalization. You have to be consistent. But for the time being, I'm not giving any interpretation, so I'm just playing around with this normalization so that I bring them to the conventional factors. So any questions up to you?
I have a rather basic question.
Mhm.
The sense that we are using a term like W sub P, is that not to confuse it with any other kind of energy, right?
What do you mean?
I mean, we with the symbol omega sub P
Mhm.
at the exponential C. The reason of using it is to not to
You see,
Mistake it with another kind of energy symbol.
well, you see, when I say E, it can be both positive or negative. I just would like to keep track of whether I have positive energy solutions or negative energy solutions. So that is why I'm defining something that is definitely positive.
I see.
That is my omega p. P meaning that it will change as a function of p. And then the energy of my energy of my wave function can be plus omega p or minus omega p. But omega p is, I define it to be positive.
I see. Sorry, I missed that definition.
Yeah. Now we have the solution of our fields. Well, let's just leave it there for the time being. Let's quantize our system. Well, how do we quantize the oscillator, harmonic oscillator? We have the P, we have the X. In classical physics, they are just functions. Quantizing it mainly means that we define the commutator to be plus or minus I. Hmm? Minus.
XP should be plus, so this one's a-
Okay, this is minus I. Okay, how do we define these x and the momentum? Well, if we know the Hamiltonian, if you know the Lagrangian, let's say we will be playing with the Lagrangian most of the time. If we know the Lagrangian, then the momentum will be just the derivative of the Lagrangian with respect to x dot. Well,
Can I ask something?
Sure.
It might be a bit, if you don't have canonical kinetic energy in the Lagrangian, then the momentum that we find is not canonical, right? It's not canonical. So what we impose as a computational relation is not canonical computational relation.
Well,
And
my understanding.
In that sense, if we do not have any constant metric, then we are not able to quantize the system because we don't have any canonical.
You see, let's not even go to that complicated case. In general, in Lagrangian, you have generalized coordinates, right? And generalized coordinates can be anything. For example, just take the free particle. It can be the Cartesian coordinates. You can use that as your generalized coordinates, or you can be the spherical coordinates as your generalized coordinates. I mean, this approach doesn't even work if you use the spherical coordinates. It just doesn't work. Yeah, we have to come up with some different tricks to quantize such a system in spherical coordinates, even if it's possible. I don't know if it's possible. So basically, we stick with canonical systems with Cartesian coordinates. We know that there, at least, the recipe works. Now, if you go back to our Lagrangian, again, let's remember the discrete case. L is equal to 1 over 2 pi squared plus, no, sorry, qi dot squared plus, no, minus 1 over 2 omega squared x qi squared. And we are summing over, well, let me say n. I'm not writing everything. So we have the momentum corresponding to the coordinate n was defined as derivative of the Lagrangian with respect to qn. Let me use m. And then what we did was, okay, this is equal to sum over n. This is qn dot derivative of qn dot with respect to qm dot. Other terms do not contain any derivatives. And then we said, okay, that derivative is actually Kronecker delta mn. If m and n are equal, that derivative is 0. If they are not equal, they are non-zero. It's just 1. This is equal to qm dot. This is what we did in the discrete case. We would like to do more or less the same thing, but there's one thing we have to modify. Now remember, we have fields that depend on position. and time. N and M, they basically correspond to different points on this one-dimensional space. So I can ask the question, what is the derivative of phi with respect to phi at a different point? Let me call this y1, this one y2, t. I can take derivative of functions at one point with respect to its value at a different point. This is, we define, this is not the Kronecker delta, because remember here, I want to obtain something that when summed over just picks up one term. That's what I'm using over there. Here I want something, I'm not summing over the coordinates, I will be integrating over them, but I still want to pick up one coordinate only. So this derivative actually becomes the Dirac delta. Similarly for the derivatives. If I have, let's say, the derivative with respect to time, this will be again just Dirac delta y1 minus y2. These are so-called functional derivatives.
Do we have some other constant that depends on the dimension in front of the deltas in higher dimensions?
Where, even here?
Yes,
No.
it's always like this, right?
Okay, let me. We can even take these as different.
Mm-hmm.
If you would like to do that, let's say.
And that just adds another one.
Yeah. But you see here, when I have the Lagrangian, I'm summing over all n, so everything is at the same time t. So basically, what this tells me is Kronecker delta mn. Remember, m and n, they're only coordinates. They specify the position of my oscillator. So this, in the continuum limit, becomes y corresponding to m, y corresponding to n. That's what I will be using now. Everything is at the same time for the time being. In my Lagrangian, everything is at the same time. What does this tell me? Okay, I have my Lagrangian. This is my Lagrangian density. If you like, the Lagrangian is just the integral of this. The momentum, this is, I will use the pi rather than p for momentum. This will be derivative of my Lagrangian with respect to phi. Let's say this is the momentum at the point y and t. I need to take the derivative of my Lagrangian at the time t with respect to my field at the position y and at the time t derivative, time derivative. And this already gives me what my momentum is. This will be just phi dot y and t.
You said this capital P was canonical momentum.
Yes.
Thank you.
Canonical momenta or canonical momentum? You know, momentum. Is there?
I would say that it's the canonical momentum. But you see, I mean, each y is actually a different momentum because it's the momentum of a different oscillator. So saying momenta also wouldn't be wrong.
Hocam, I guess beforehand we took Lagrangian mass term as class. I'm not sure, but I remember that.
Okay, at least it doesn't change this one. I think it should still be minus. I did some mistake somewhere else. I mean, that term should be minus. Anyway, let me finish this argument, and I will go back to my previous derivation. It should be minus. Okay. Anyway. Now I have my commutation relation. Okay, you see, this was my commutation relationship. I can have different, now I have many oscillators, each one have its own coordinate and momenta. So if I have the momentum of one oscillator and its commutation with the coordinate of the other oscillator, it should be 0 if they are different oscillators, it should be minus I if they are the same oscillator. So this is my commutation relationship in the discrete case. Which will become, well, pi at the point y1 of t, phi at the point, let's say, y2 of t. This should be equal to minus I Dirac delta y1 minus y2. These are so-called equal time commutation relations. For the obvious reasons that they are evaluated at the same time t. Now we will calculate what this commutator will be if the time t are not equal. So basically this is our quantization. Now we will see what this means. Okay, in the next hour, what we will start doing is, let's say we have these commutation relationships. Well, I have my field. I can write my field in this way. I will see what those commutation relationships tell me about these phi of p and phi star of p. Then a nice picture will start to emerge. Any questions before you go for a break?
Can I ask something in the break?
Always. Okay, so see you in 10 minutes. Go and have some coffee, and see you later.
Şey,